Hello students, today we will discuss nucleophilic substitution reactions. So without wasting time, let's start with the question that what is a nucleophilic substitution reaction? So let's suppose methyl chloride reacts with potassium hydroxide and it forms methanol and KCl. So what is happening in this reaction is that this Cl has been replaced by OH. Clearly this Cl has been replaced by hydroxide. ठीक है? So these type of reactions when a negatively charged hydroxide, in this case nucleophile, replaces the leaving group. What is the leaving group now? It is chlorine negative, are called nucleophilic substitution reaction. The outgoing group, in this case outgoing is Cl, this is called a leaving group, and the incoming group, which is OH or hydroxide, this is what we call a nucleophile. Moving further, what are the types of nucleophilic reactions? Basically we are concerned with only two types, SN1 and SN2 reactions. How they are different? Order of SN1 is 1, in case of SN2 the order is 2. How they are different? The mechanism of both these reactions is different. So now we will study how SN1 is different from SN2, and we will discuss both these mechanisms in detail. Now starting with the SN2 mechanism, one thing you should note, this is a single step mechanism. All the process occurs in a single step, and this mechanism involves formation of a transition state, and third, SN2 is mostly found where molecule is small or less bulky. For example, methyl chloride and KOH reacts to give methanol and KCl. What happens is this, that the nucleophile, which is hydroxide negative, attacks the carbon to which leaving group is attached from the backside. So this is the main thing. Attack is from backside. Nucleophile attacks from the backside or 180-degree angle from the leaving group. As the attack occurs, a transition state is formed in which this chlorine is now leaving the molecule and bond with OH is being formed, and for the time being the carbon adopts a hybridization which is similar to the planar geometry, and once the reaction is complete, methanol is formed. Now one thing you can note is, now OH and Cl, they are placed on opposite side. Now Cl is on the right side of the reactant, whereas in case of methanol the OH group is at the left side of CH3 in the representation. This is what we call inversion of geometry. That is, where Cl was present at the starting of the reaction, OH now occupies exactly opposite position. This is what we call inversion of geometry. Now moving on to, since this reaction involves only single step, then the rate can be written as K Rx, Rx for this CH3Cl and nucleophile. Now since only these two species are formed, the order of the reaction is 1 plus 1, 2. Therefore, we term it as SN2 mechanism. Substitution, S stands for substitution, N stands for nucleophilic, and 2 stands for biomolecular. That is, the order of the reaction is 2. Now we will consider what are the factors which affect the rate of SN2 reaction. First and the foremost is the steric hindrance. Steric hindrance means lack of space or repulsion due to overcrowding. So let's take example. In this reaction, CH3Cl, then in the second step we have CH3CH2Cl. In the third example, we now have CH3CHCl CH3, and in the last example we have CH3CH3Cl. So without naming them, we can clearly see this is primary, This is secondary and the last one is tertiary. If you are interested in their names, it is tertiary butyl chloride, secondary isopropyl chloride, this is ethyl chloride. Now consider the reaction of hydroxide with all these four molecules. Let's zoom in for all these. In first case we can write this CH, H, H, Cl. In the second case we can write CH3, H, H, Cl, and similarly we have written for secondary and tertiary. Now in case of SN2 reaction, the attack of the nucleophile should occur from a direction which is opposite to Cl. Now again in this case here, in the third case here, and same in the fourth. Now if we look more closely, just consider hydrogen is the smallest atom. Therefore, it occupies least space. But CH3 is larger and has greater electron density. Clear? So what is the role of electron density? In case of electron density, the incoming nucleophile is negative. If there is more electron density, then there are going to be forces of repulsion. Now look closely. Here all three are hydrogen, which are the smallest. So this case no repulsions occur. That means there is easy approach. It can go through the yellow path and knock Cl out of the molecule. But now in case of secondary, this CH3 group is present. Now due to this, there are going to be some repulsions. In case of secondary, now there are two CH3 groups, greater repulsions, so this hydroxide OH will face difficulty to reach carbon. So this is going to be now slow. In this case, this was going to be still faster. Now in the last case, now we have three repulsion, three CH3 groups, greatest repulsions, and this OH is not allowed. No backside attack, side attack is possible. Thus, no SN2. Therefore, what we can summarize is that in case of SN2 reactions, methyl substrates are faster than primary substrate, which are in turns faster the secondary substrates, and in case of tertiary substrates the reaction is slow. In the order SN2 mechanism, rate decreases, and in case of tertiary there is no SN2 in case of tertiary molecule. Let's now discuss SN1 mechanism. What are the key features of SN1? This reaction occurs in two steps. It involves the formation of a carbocation. Role of nucleophile is limited or minimum, and at last retention of configuration is achieved. So let's discuss what happens in SN1 mechanism is that in step 1 the leaving group departs from the molecule on itself and results in the formation of a carbocation. This is what we call a carbocation in which carbon has a positive charge. So what is the first step? First step is formation of carbocation. So from here there is a question, why does leaving group leave without nucleophile? The answer is simple, because now it's more stable due to the formation of a carbocation. So what is the second step in this reaction? Step 2. Now once the carbocation is formed, then the nucleophile attacks the carbocation as shown below. This is the carbocation now attacked by the nucleophile to give you the final product. What is the final product? In which nucleophile has replaced the leaving group X. Now since there are two steps, the first step is slow and the second step is fast. Now in such case rate is determined by the slower step. Reaction step. Therefore in this case rate is equal to K, and in the slow step there is only one reactant. So rate becomes K into Rx. Since the order is now 1, that is order is 1, therefore we term this mechanism as SN1, substitution nucleophilic unimolecular. Unimolecular indicates that order of this reaction is 1. Now let's discuss how the structure of the reactant affect the rate of SN1 mechanism. To explain, once again we will go back to our all these examples which we have discussed in the case of SN2. Isopropyl chloride, and in the last case we have tertiary butyl chloride. Now simply write the carbocation which is formed by all these three. This is methyl carbocation, this will form ethyl carbocation, this will form isopropyl carbocation, and the last will form the tertiary butyl carbocation. Now this is primary, this is also primary, this is secondary, this is tertiary, and we know that tertiary are the most stable and methyl and primary are least stable carbocations. Now why we are studying this? Because in case of SN1, the first step is the formation of carbocation. Therefore, if carbocation is stable, the rate of first step will be greater. जितना ज़्यादा ये स्टेबल होगा उतनी जल्दी ये फर्स्ट स्टेप कंप्लीट होगा हमारा. Therefore, if in the first step methyl carbocation is formed, then the reaction is going to be very slow, same as case of primary, and when the carbocation is stable, the rate is moderate, and the rate will be the fastest when tertiary carbocation is formed. Therefore, in case of SN1, CH3X will be slow than RCH2X, that is primary, which further will be slower than secondary alkyl halides, and the fastest will be the tertiary alkyl halides in case of SN1 reaction mechanism. I hope this answers all your questions regarding nucleophilic substitution reactions and SN1 versus SN2 reaction mechanism.